Hello, my name is Jennifer Wiseman. I am the Senior Project Scientist for NASA's Hubble Space Telescope mission based at the Goddard Space Flight Center. Today, I want to tell you about what we're excited about in the coming years as we anticipate Hubble's new era of discovery. The Hubble Space Telescope was launched in 1990 on the Space Shuttle Discovery. Here you can see that fabulous launch image. And here are some of the stats on Hubble. It is moving at about 17,000 miles an hour in low Earth orbit at about 340 miles above the Earth's surface. It takes data and transmits the data back to the ground while receiving commands from the ground. It can keep very stable pointing. The reason that we keep Hubble in low Earth orbit above the Earth's atmosphere is so that we don't have to deal with the blurring and filtering effects of the atmosphere on astronomical images. So here's an example of the core of a globular cluster of stars in the Milky Way, Omega Centauri. And because Hubble is above the blurring effects of the atmosphere, we can differentiate star from star, even in a very crowded cluster like that, seeing beautiful colors and the differences between stars with different outer temperatures and different brightnesses. And so we've become spoiled over the years with images like this. Here's a glorious star-forming region with a massive cluster having formed out of interstellar gas and dust, and the radiation from these massive stars going back into the surrounding leftover gas, ionizing it and giving us these beautiful colors, indicative of beauty and ongoing activity in our galaxy. And here's a spectacular image of a carbon star, CW Leonis, we released this year as a Halloween image because these outer expulsive layers of the star look like a cobweb around the bright center. Astronaut servicing of the Hubble Space Telescope Observatory has enabled repairs and enhancements of the mission over the decades. 5 times astronauts have gone up to either repair components or put in newer cameras and instruments. That's enabled not only mission life extension for over 31 years now, but also keeping Hubble at the forefront of scientific return. Hubble is thankfully in good technical condition overall and is therefore at the peak of its scientific return even now. It's a full observatory with a powerful suite of cameras and spectrographs, and we have a wonderful team of technical experts on the ground that can address any technical glitches that come up from time to time, even though we don't have the space shuttle anymore to take astronauts up for hands-on repair. Often we can address issues through commanding from the ground. And I'm always intrigued by the expertise of this team that seems to be able to understand every glitch and be able to get us back to science very soon. Hubble has panchromatic capabilities. It can observe in different kinds of light, visible light and also ultraviolet light, and even into the near infrared part of the electromagnetic spectrum. This enables us to learn more about the objects we're studying than we could if we didn't have all those capabilities. For example, the Eagle Nebula here, famously known as the Pillars of Creation. You can see on the left in visible light, as these dusty pillars are carved out by the winds from stars that have already formed off the top of this image. But we'd like to see into those dusty pillars, and we need infrared light to do that. So on the right, you see Hubble's infrared camera, able to peer through that dusty veil and see many more stars and see into those pillars where lower mass stars, which take longer to form, are coalescing and heating up, especially at the tips of these dense pillars. Different kinds of light give us different kinds of information. Hubble's capabilities complement the capabilities of other space-based telescopes and telescopes on the ground and even probes. So here's some examples. There's Hubble on the top, the Keck Observatory on the lower left, the ALMA radio millimeter and submillimeter observatory on the lower right. These are observatories with different capabilities, different wavelength ranges they can reach, different fields of view, and together they give us a more complete picture of what we're trying to study, be it the solar system or other galaxies, or the universe as a whole. So we're looking forward to these complementary capabilities between Hubble and other telescopes and probes for exciting scientific return in the coming years. Hubble's unique capabilities and this complementarity enable new innovative exploration of the universe, both near and far. So we'll be using Hubble to continue to make new discoveries about our solar system, about stars and their planets, about galaxies and the interstellar and intergalactic medium, and even the universe as a whole through cosmology. And Hubble is starting to investigate big questions about the universe that were originally unanticipated when Hubble was launched, or it was unanticipated that Hubble could address them. Things like our dynamic and sometimes surprising solar system, even addressing questions about whether there could be planetary systems like our solar system around other stars. And what about dark matter? Where is it? And what are its effects? And what are the effects of dark energy? Hubble is even observing radiation from sources of gravitational waves. Let me show you some examples of these things. Here are the newest images from Hubble's program of watching the outer planets in our solar system year after year, the Outer Planet Atmospheres Legacy Program, or OPAL. And here you can see these magnificent recent images of Jupiter, Saturn, Uranus, and Neptune in great detail. Because Hubble has been observing the planets over and over again for decades, we can see planetary weather and atmospheric changes in these planets over time. And indeed, that is what we're seeing. In Jupiter, for example, we know that the Great Red Spot, the giant storm, has been shrinking over the years Hubble has been observing that spot. And now we also know that the wind speeds are changing. Here you can see a side-by-side showing that the outer part of the Great Red Spot, the wind speeds have increased by 8% since 2009, and the inner wind speeds are significantly slower. We're using Hubble in complement with the JUNO probe to study details about Jupiter's environment and storms. Here's a comparison of what we can see using Hubble's detections of reflected light from storms on Jupiter with JUNO's reception of radio waves from storms and lightning deep within these storm clouds, and using that in complement with the Gemini ground-based observatory's detection of thermal infrared emission. All of this together gives us a much more complete picture of what's going on in Jupiter's storms. Hubble provides the only general ultraviolet light observing capabilities in astronomy now or even in the near future. So here's a visible light image of Jupiter, but superimposed now is the ultraviolet light capability that Hubble can see. And this is showing us the bright aurora here on the northern pole, where particles from the sun are interacting with Jupiter's magnetic field and lighting up, similar to the northern lights on planet Earth. By having Hubble able to see both visible and ultraviolet light, we can monitor this phenomenon and compare it with what Jupiter is measuring right there, what JUNO is measuring right there in situ as it measures Jupiter's magnetic and gravitational environment. Hubble is also studying our solar system and objects that are whizzing through but originated in other star systems. So here's an artist's conception of the asteroid Oumuamua, which is an object generated from another star system. We can tell from its trajectory that passed through. Hubble did not discover the object, but has been doing follow-up studies, as well as Comet Borisov, again, seeming to have been ejected from another star system. And this comet is very carbon rich, so it tells us something about other star systems compared to our own. We anticipate in the coming years, more and more of these interstellar objects will be detected with other observatories, and then Hubble will do the detailed follow-up. Hubble is the pioneer in analyzing the composition of atmospheres of exoplanets, and we're continuing to do a lot of exoplanet atmospheric analysis with Hubble, and we'll continue to do so. We've detected things like sodium and even water vapor on many exoplanet atmospheres through transit studies. And these complement the observations of observatories like TESS and the future James Webb Space Telescope. Hubble looks at other galaxies. In fact, Hubble even looks at whole groups of galaxies and studies things that we cannot see. Here's a large cluster of galaxies. The most massive gravitationally bound entity that we know of are these large clusters. And most of the mass in these clusters is not visible in the galaxies. It's dark matter. This dark matter is significant enough to even distort space-time. And we can see the effects of this dark matter by seeing how light from background galaxies is distorted and magnified as it comes through the region of distorted space in the cluster. So here, if you look closely, you can see these weird-looking arcs of background galaxy light coming through. That tells us something about how the dark matter is distributed in clusters, even though we can't see the dark matter itself. And this gravitational lensing effect also magnifies background galaxies, so we can see some detail of very distant galaxies that are shining to us from the very early universe. Here's an example of a galaxy whose light began its journey just 500 million years after the beginning of the universe. We're seeing within the 0.8 of the 13.8 billion year history of the universe, we're seeing into that first 0.8, the first few hundred million years, and seeing how young galaxies began to grow. Here's the ultra deep field of Hubble, famous for this field of galaxies we can see within a small field of view. Some of them are closer to us than others. And so the ones that are farther away, we're actually seeing them as they were earlier in time. So astronomy is like a time machine. And here you can see how over time, from top to bottom here, as observatories and cameras within the Hubble have improved, they've become more sensitive to more distant galaxies. That's what the arrows are showing. And that's equivalent to looking farther and farther back in time. The timeline on the bottom shows that we're now seeing to within a few 100 million years of the beginning of our universe, of the Big Bang. The Webb telescope should be able to see even earlier galaxies and proto-galaxies, because that light traveling through expanded space gets redshifted far into the infrared, where the Webb telescope can pick up those baby galaxies. There is the Webb telescope in the clean room at the Goddard Space Flight Center as it was being put together. And here's a side-by-side comparison. You can see the Hubble on the left with its 2.4 meter mirror, the Webb telescope on the right with its 6.5 meter segmented mirror, and their different wavelength capabilities. So Hubble sees ultraviolet and visible colors of the rainbow and into the near infrared. The Webb telescope sees red light and farther into the infrared. So these observatories will be complementary. We're very excited to have both of them operating, hopefully for several years of overlap, to give us complementary scientific results. And I'll mention that the Roman Space Telescope, named for astronomer Nancy Grace Roman, is coming later this decade. It has the same mirror size as Hubble, but a much bigger field of view. So you can see the footprint of Roman there on top of the background galaxy compared to the smaller postage stamp fields of view of Webb and Hubble. Roman will be good for surveys of large swaths of the sky, and it will be an infrared telescope. You can see the wavelength coverage comparisons of the three observatories at the bottom. These observatories will complement one another. We're even looking forward to seeing more transient events. Hubble can, for example, observe the electromagnetic radiation that accompanies some gravitational wave events. So in this case, what you're seeing is a pair of neutron stars that merged, created a gravitational wave event that was picked up by LIGO detectors on the ground. But the event was also accompanied by a kilonova explosion that Hubble observed through its ability to detect electromagnetic waves. And you can see the explosion there as Hubble saw it, its context in the galaxy, and how it faded over a few days from being very bright back in 2017. We anticipate more of these detections in future years. We also anticipate that a lot of Hubble discoveries will come from its archive. Already, scientists are mining Hubble's archive of data and publishing papers. At least half of the peer-reviewed scientific papers from Hubble are based on archival data even now. And so this makes us very pleased that Hubble data is being well used, sometimes for different varying scientific purposes. And even after Hubble's observing mission is over, new discoveries will continue based on this robust archive of Hubble data. Hubble will continue to inspire in many ways, both scientists and the public through images. Here we see tactile images. We see images in stained glass based on Hubble images. We see even popular images on moving vans. And so we are excited. We anticipate that Hubble will continue with strong scientific capability, likely through the 2020s and hopefully beyond. And its scientific capabilities will complement future missions like the James Webb Space Telescope and the Roman Space Telescope. If you want more information, check out our website, nasa.gov/Hubble, and the other sites you can see here. And we're active on social media at NASA Hubble. Thanks for your interest, and let's wish Hubble a very happy 31st birthday and many more to come. Thank you.